Good morning, everyone. I am Prashant Kumar. Today, I am going to talk about fundamental parameters of antennas. This is the second lecture I am giving in this antenna series. Previous class, I have discussed about what is an antenna, how does it work, what is its definition, and I also discussed about the syllabus, what type of antennas you are going to study, what are the applications, what is wave propagation. Now, after this, the first unit talks about basic parameters of antennas. So, in this video lecture, I am going to explain about what are the fundamental parameters of antenna. Before going into the details of these fundamental parameters, I would like to explain about what are these parameters. The first parameter is radiation pattern, radiation power density, radiation intensity, beam width, directivity, numerical techniques, antenna efficiency, and gain. All these parameters are called as fundamental parameters of antenna. Along with this, we have other parameters also that we can talk about later. Now, yeah, you can see beam efficiency, bandwidth, polarization, input impedance, antenna radiation efficiency, antenna effective length, directivity, effective area, Friis transmission equation, and radar range equation, finally antenna temperature. All these parameters are called as fundamental parameters of antenna. Before going into these parameters, I would like to discuss about radiation pattern. Before going into the radiation pattern, as I told you, we should have a prerequisite knowledge about electromagnetic systems. We have three types of coordinate system. One is rectangular coordinate system, second one is cylindrical coordinate system, third one is spherical coordinate system. Normally, the antennas are placed at a height from the surface of the earth. So, they are almost located in the air. So, here we are talking about, we consider spherical coordinate system as effective coordinate system for dealing with antennas. Now here, if you observe carefully, here in this diagram, we can see about spherical coordinate system. What are different parameters in a spherical coordinate system? The distance from the origin to the point of observation, that is radius, and the angle, horizontal angle is called as azimuth angle, and the vertical angle is called as elevation angle. Based upon this, here I would like to explain about this diagram, which is very important because it helps us to calculate power. It also helps us to calculate area and many things. Now, if you look here, this is called as radiation pattern. Radiation patterns are of two types. One is directional pattern, second one is uh, which radiates in all directions, that is called as omnidirectional pattern. Now, if you look at this particular diagram, it is a spherical coordinate system, it is a sphere, and here this is the projection to the horizontal plane. XY plane is called as horizontal plane, and this is the Z axis. Now, the small area on this surface is called as dA. How do we calculate this area? So, this is like a sector. This side it is a curved surface, and this side it is also a curved surface. Now, the angle this side it is theta, starts from here and it ends up to 180 degrees. Similarly, the angle pi starts from here and at 360 degrees. So here the angle is theta, and the smallest angle here is d theta. Here the smallest angle is d theta. So the radiuses are into smallest angle. So this side is called as r d theta. We want to know about this side. What is this side? That is r sine theta into d phi. The angle in this direction is phi and the smallest angle is d phi. And here this length is r sine theta. So multiplying radius with angle, that is d phi, we are getting r d theta into d phi. This is r d theta into r sine theta into d phi. This is r d theta. So multiplying these two, we are getting smallest area as dA equal to r square sine theta d theta d phi. Now here we need to understand about what are the coordinates, what are the vectors. In the direction of theta, we have a theta. In the direction of phi, we have a phi. In the direction of r, we have ar. Similarly, the electric field component and magnetic field component in the direction of r is er and hr. In the direction of phi, it is e phi and h phi. In the direction of theta, it is e theta and h theta. So this always is the standard representation of calculating the fields in antennas. So this plane is called as elevation plane because it is vertical plane, and this is called as azimuthal plane. It is also called as horizontal plane. Having understood about this, we are going to calculate the surface area of a sphere. So we have r square sine theta d theta into d phi. If you integrate them over theta and pi, what are the limits for theta 0 to pi, and what are the limits for pi 0 to 2 pi? So if you integrate them, what is the area we are getting? 4 pi r square, which is nothing but the surface area of a sphere. So coming to radiation pattern, we can define it as it is a mathematical representation, graphical representation. It is a polar graph of radiation properties of an antenna, like how the field or how the amplitude varies as a function of theta and pi. So here the amplitude can vary, or phase can vary, or polarization can vary as a function of theta and pi. For example, we studied in mathematics what is f of x. F of x means it is a function and x is a variable. So similarly here the function radiation pattern varies as a function of theta and pi. Next, field pattern and power pattern. Field patterns generally calculated in terms of E of x theta comma phi. Similarly, h of theta comma phi. Power pattern, it is the square of the field, E square or h square, and they are calculated in decibel square. So what is field pattern? It is how the variation of electric field and magnetic field. And what is power pattern? It is the square of electric field and magnetic field. Next, here you can see is a radiation pattern. This is called as major lobe. Many students, they ask what is the meaning of radiation pattern. Radiation pattern means what is the direction of radiation. Here we can see the antenna is radiating in the topwards, above direction. Similarly, there are some minor lobes also, and this is called as back lobe. Along with main lobe, we have side lobes. So what we need to do is we need to check that the main lobe radiation is maximum. Main lobe radiation is maximum. So based upon this field pattern, we can calculate the important parameter, that is half power beam width. So if you look at this radiation pattern, this is a normalized pattern. See here, you can see normalized pattern. What do you mean by normalization? Dividing the component with its maximum value. For example, if an antenna is radiating 30 megawatts of power, if you try to plot from 1 watt to 30 watts, the graph becomes very large. So what we try to do is we normalize it. That means we divide with its maximum value. 30 by 30, it is 1, and remaining values will be less than 1. So it is varying from 0 to 1. So here the maximum value is 1. It is the center. With respect to this maximum, we are going to calculate half power beam width. What is half power beam width? It can be defined as the angular distance between half power points. See, with respect to maximum, these 2 points are called as half power points. Many of you will get confused. Half power means 0.5. It is not 0.5. It is 3 dB point. So here, with respect to maximum, the power is becoming half here. Similarly, half here. So the angular distance between these two half power points is called as half power beam width. Now it is the radiation pattern of 10 elements, and the spacing between the elements is lambda by 4. So we got half power beam width as 38.64. You can ask me what is the importance, what is the significance of this half power beam width. The significance is the maximum power will be concentrated within this half power beam width only. Sometimes we take a mobile phone and we get very weak signal. That means if the signal falls in this range, that means the signal is very weak. These points where the intensity is 0 is called as null points. Some places we don't have any intensity. They are called as null points. So I think you have understood what is half power beam width. Next, this is normalized power pattern. So I already told you power means it is the square of E or H. So it is narrower than field pattern. So if you take linear scale n equal to 10, the distance between the elements is lambda by 4. So the half power beam width became 38.64. Previous it is 38.64, and here it is 38.64. Now normalized power pattern of a linear array. So this diagram explains us about the radiation pattern of an array antenna. So array antenna is basically used to improve the gain, but the disadvantage is there are side lobes. So not only side lobes, there are many lobes that are coming in the way. So in this diagram, what we are observing is there are many side lobes. I will tell you the technique how to minimize these side lobes and concentrate the radiation in one particular direction. See here, we define one more new term called as first null beam width. I already discussed about half power beam width. So to see, if you look at this pattern, this is called as polar pattern. Polar pattern means it is the graphical representation of variation of field or power in the direction of theta or phi. So first null beam width is defined as the beam width between first null points. This is one first null point and this is second first null point. So the angular distance between these 2 points is called as first null beam width. Similarly, the angular distance between these 2 points is called as half power beamwidth. You can see this is called as major lobe, and these are all called as minor lobes or side lobes. Always see that in antenna design, very important observation is the side lobe should reduce because the power is unnecessarily radiating in these directions. So it is a polar plot and this is the rectangular plot. It is x comma y. Here x-axis is angle and y-axis is radiation intensity. From this we can calculate where it is half power beamwidth and fresnel beamwidth. Now it is a three-dimensional pattern. Always the fields are represented in three-dimensional pattern. Generally we may not be observing directly in three-dimensional pattern, but in reality it is a three-dimensional pattern. See here, this is the main lobe and these are side lobes. So here, if you use a software and plot the radiation patterns, we can always see them in three-dimensional way. So it is the field pattern of a linear array where the number of elements is 10 and the distance between them is lambda by 4. Here the distance and phase plays a major role that I will explain in third unit what is the importance of distance. See here, E is a function of r comma theta comma phi. That means E is having component in the r direction, E is having component in the theta direction, and E is also having component in the phi direction. So the vector E can be represented as, it is the magnitude square root of ER square plus E theta square plus E phi square. Next, amplitude radiation patterns. They can be isotropic, directional and omnidirectional. Isotropic antenna is, for example, sun. How the sun radiates? It radiates in all directions. Sun radiates in all directions. So generally there is no isotropic antenna, but we always consider, take for example here, I want to explain you about uh, a simple example. See, this is a sun. See, sun, it radiates equally in all directions. Sun radiates equally in all directions. This is the radiation pattern. How it is the radiation pattern? It is a circle. Here some curve has come, but in actual it is a circle. If you take a three-dimensional pattern, it is a sphere. It is a sphere. Take for example a bangle and rotate it three-dimensionally. What type of radiation pattern you are getting? Sphere. Ideally there is no isotropic antenna, but we consider these antennas as we consider sun as isotropic antenna. Second one is directional antenna. What is a directional antenna? See here, if you see this diagram, it is a horn antenna. Horn antenna all of us have on the top of our home. So the radiation is in the forward direction. This is called as directional radiation pattern. This is the E field, vertical one, and horizontal one is H field. Always both are perpendicular to each other. Next one is omnidirectional pattern. Omnidirectional pattern is the the pattern which is in only one direction. It is having the shape of a what to say, you all of you know this one. In bakery we have this, I'm not exactly remembering, but so if you take, I will draw the omnidirectional pattern here. like this donut. Yeah, donut. So this donut, in Telugu we call it as gare. What is the shape of donut? In the center, free space, and around this. So if the antenna is vertically placed like this, the radiation is concentrated around that antenna in one direction. Here it is a horizontal direction. So it is called as omnidirectional radiation pattern. If the antenna is horizontal like this, the radiation is around like this. I think you are able to understand. So this is called as omnidirectional radiation pattern. Okay. So coming to our radiation patterns, next one, principal patterns. There are two principal patterns, E-plane pattern and H-plane pattern. Then pattern lobes. I already explained what is main lobe, what is side lobe, and what is back lobe. See, this is omnidirectional pattern. See, if the antenna is vertical, so around that antenna, it is having the shape of a donut. See, this is E theta, and perpendicular to E theta is always H pi. See the radiation pattern in three-dimensional. Very easily we can understand this. Now, field regions. What are different field regions? There are two field regions. One is near field and one is far field. Near field is the region near to antenna. Here we are basically calculating from a formula called as 2d square by lambda, where d is the maximum dimension. If you substitute the length of the antenna here, we get R2. So less than R2 is called as near field and more than R2 is called as far field. Right? These are the two field regions. So based on that, we have certain observations, how the field will be in the near and how the field is far direction. See, this is the near field and this is far field. So I think with this, I have explained about the basic parameters of an antenna, and our next class I will be explaining about remaining parameters. Thank you.